Hello everyone, I'm Syed Zawad and I'm a PhD student at the University of Nevada, Reno. Today I'll be co-presenting our paper TIFL, a tier-based learning system, along with my co-authors Zheng and Ahsan. For this work, we demonstrate the effects that data and resource heterogeneity have on federal learning systems, and based on these observations, we propose a system that can reduce the training time of federal learning processes without compromising model accuracy by using an adaptive scheduling policy. So generally speaking, the more data we have for training means better machine learning models, and one of the best sources of data are from the users themselves. For example, if you want to have a machine learning model for autocomplete, we train on user-type texts, and for cancer detection, we train on cancer patient data, and so on. So usually we do this by accumulating the data sets in a single database and use a cluster to train our models on them. However, allocating user data centrally has certain privacy implications, and in addition to that, there are laws that actively prohibit user data to be seen by third parties or used without consent. As such, training on user data using the traditional method has become somewhat infeasible. To address this problem, federated learning was introduced. The main idea of federated learning is to collaboratively train a machine learning model without actually sharing or revealing data to the training servers. There are two ways of doing federated learning. The first one is cross-silo, where institutions with user data, such as hospitals and banks, train models collaboratively without seeing each other's data. And the other way is called cross-device federated learning, which is what we focus on in this project. So federated learning was introduced in this paper in 2016 called Federated Learning, Strategies for Improving Communication Efficiency. In this setup, we have an aggregator server and a set of edge devices containing the data. And the server contains a global model, which will be trained on these edge device data. So in one round of training, we start off by randomly selecting a subset of devices from the full pool of available IoT devices. And then we send our global model to the selected devices and ask them to train it. So, and then the devices locally train the global model on their own individual data sets, and then generate their own local models. And these model parameters are then sent back to the aggregator server with some noise and encryption added for privacy. The server waits until it gets a reply from all the selected devices, making this a synchronous process. Once it receives all the updates, the aggregator applies the federated averaging algorithm on them to generate a new global model. So this federated averaging algorithm is basically just an average of the parameters of the models, and it gives increased weights to models trained on a higher number of data points. So once we have this new global model, after averaging, we start the next round and training proceeds like before. So there are a few challenges that are unique to this federated learning system. First of these is due to the sheer diversity of IoT devices. Federated learning systems can sometimes take place with millions of devices, making it an extremely large-scale distributed learning system. These devices can range from HPC clusters to smartwatches, meaning that a wide variety of hardware could end up being used for training, which then results in a wide variety of training times, even for the same model. We term this diversity in training resources as resource heterogeneity. The next problem with federated learning arises due to user habits. For example, if a person likes to text a lot, their phones will likely have much more data points than someone who doesn't text at all. So because of this, the local amount of data points varies between devices, and we term this variation as data quantity heterogeneity. And lastly, we have the issue of quality data being present in devices. This again is dependent on the user preferences. Like for example, if you're a cat owner, it's likely that you have more images of pictures of cats in your devices than you have pictures of dogs. So if you were to train a model on that data, the model might end up being very good at classifying cat images, but really bad at classifying dogs. So this results to a biased local model. And we call this diversity in data features as data quality heterogeneity. Since this level of heterogeneity is almost uniquely a property of federated learning systems, so other systems also have heterogeneity, but not at this scale. This question arises, how does this heterogeneity matter? To understand this, we ran an impact study using CyPROC-10 dataset. So this graph here, we show the training time for CyPROC-10 with different data quantities and CPU resources. First, if we just look at how the training time changes with CPU resources with the same data points, for example, just the black bars, we see that training time increases almost linearly with reduced resources. Next, if we keep the CPU resources constant and focus on varying the data points, say if we observe for the 4 CPU cases only, we also see that increasing the number of data points significantly increases training time. And so based on these observations, we can say that the resource and data quantity heterogeneity impacts total local training time. Since federated learning is a synchronous process, the slower clients will cause this whole training process to lag behind, which is why we call these loyal clients the stragglers. For the next experiment, we explored the impact of data quality on model performance. Over here, we shorted the Cypher10 dataset into 50 parts and assigned each part to a device and used them as IoT devices for better learning. We reduced the data quality by reducing the number of classes available in each device, which makes the local dataset highly biased. For example, non-ID2 here means 2 classes of images for every client, which is more biased than non-ID10 or non-ID5. As we can see from the results, if we decrease the non-IDs from 10 to 2, that is to say we increase heterogeneity, we observe a drop of around 10% in accuracy, which is significant. And so based on these results, we conclude that data quality impacts model performance. Now, we did a little literature search on how the state-of-the-art solutions tackle these heterogeneities. We present 3 of the most important ones here, but I won't go into the details for each of them due to time. But the takeaway here, based on our review, was that the state-of-the-art systems focus on handling stragglers by dropping or partially training on them, and do not consider the data heterogeneity at all, or its impact on model performance. So since no existing system fully takes this into consideration, we decided to tackle this problem and came up with TIFL, which is a fair learning system that mitigates the training time delays that occurs due to stragglers without actually compromising model accuracy. And now I give the floor to Zheng, who will present the details of our proposed system. Thank you.
Hello everyone, my name is Zheng. I'm a PhD student at the George University. In the following slides, I will introduce the system design of TIFL and how it works. This figure shows the overview of TIFL. We'll add 2 additional modules on top of the traditional federated learning system. A profiler is added for profiling the client's training latencies. Then based on these latencies, clients are divided into logical tiers. Next, we have a tier scheduler, which is responsible for selecting the clients during the training process, such that the total training time is controlled. Let's take a look in detail how the profiler works. We'll have an aggregator with a global model and IoT devices. This part is as same as the traditional federated learning. At the beginning of training, we start the profiling process by first sending a global model to all the available clients. Once clients receive the global model, clients start to training process locally. Once clients finish training, they acknowledge the aggregator. Then the aggregator calculates the training latency for each client. The aggregator then stores these profiles in a local database. The profiling can be done online as well. The profiler keeps track of how long a client takes to train. So whenever a client gets selected for training in a round, and it deviates from its training time profile, the server can notice change and update the profile. Once we have the complete profile information of all the clients, we start the tiering process. We do this by creating a histogram of the training latencies of the clients. We then create a certain number of bins, and the clients that fall within the bin, within the same bin put in the same tier. The number of bins is set by the user and determines the number of tiers. For example, here we have 5 tiers, and every tier contains devices which have similar latencies to each other. The training latency equals to the local training time plus the network latency, so we make low assumptions on client's local data. Each of clients can have different number of data, and so clients within same tier can have a variety of data features. For example, suppose we have assigned tier 1 probability of 0.3 and tier 2 a probability of 0.2. If we train for 100 rounds, tier 1 will be selected around 30 times, and tier 2 will be selected around 20 times. So if we assign higher probability for faster tiers, we could speed up the total training time. The aggregator select one tier based on the probabilities. Then select subset of clients from that tier for training randomly and perform the training process. So while tiering could save total training time, in traditional federated learning, we randomly select from all available clients. And in a round, we can have a wide variety of different training times. Since the round is synchronous, it's always bounded by the slowest client selected in that round. So we will have high probability to have slower per round training time. However, by tiering, we group the clients with similar latencies together. So clients within a tier to have close training time. Then we randomly select a tier, and then we randomly select clients from within that tier, meaning that we select clients that have close training latencies. So if we use tiering, the per round training latency is up-bounded by the slowest client in that tier, rather than the slowest client from all available clients. As such, by grouping clients based on latencies into tiers, and then selecting clients from that tier only, we can actively control the time per round and so the total training time. We evaluate our naive selection policy on two datasets, Zawad and Feng. For the sake of resource heterogeneity, we deploy each client on an instance on AWS, varying the compute resource from 4 CPUs to 0.2 CPUs. For Zawad, we deployed 50 clients. For Feng, we deployed 182 clients. We defined 5 different tier selection policy. Vanilla is the policy for traditional federated learning. Policy slow means we only select the slowest tier. Uniform means every tier has the same probability. For random policy, we assign a faster tier, high probability, and low probabilities for the rest 4 tiers. The fast policy means we only select the faster tier. We first evaluate the performance of TIFL's Strobel selection policy in terms of training time and accuracy in a resource heterogeneity setting. All the clients has the same amount of data. We can observe that the fast policy could achieve 10 times training time improvement comparing to vanilla policy. We also compared the accuracy over time. We can see from the chart on the right hand, the fast policy could get 6% higher accuracy. It's because the fast policy is able to train more rounds. We can conclude that in a resource heterogeneity environment, TIFL improves the training time significantly with high model accuracy comparing to vanilla federated learning. In data quantity heterogeneity setting, each client has same resource, but a different amount of data. In terms of training time, the fast policy get 2 times speed up comparing to the vanilla federated learning. In the case of model performance, the fast policy could get a suboptimal accuracy. This is because the client in the slowest tier has more data points. So the fast tier only uses a small part of total data points for training. We evaluate a more practical case of federated learning where we combine resource and data heterogeneity. In the case of training time, the faster policy could get 10 times improvement comparing to the vanilla policy. With a training budget of 12,000 seconds, the fast policy outperforms the vanilla policy by almost 5%.
Thank you, Zheng. Now let's look at some of the drawbacks of the static tier selection policy. We observe there is a trade-off between the model performance and the training time. This usually happens because of two main reasons. First one, the data quality is not known in advance. The second one, training latencies can vary due to data quantity or the resource availability. High latencies can be impact of large amount of data residing in the clients. Excluding these clients from the training process may impact the model performance adversarially, even though it improves the overall training time. Also, prioritizing some tiers over the other tiers can cause the model biasness. What that means is, if you only select the client for the faster tier, the model will be performing better for the faster tier. On the other hand, the lower tiers will perform worse, eventually leading to the lower model accuracy. We also observed there was no single static selection policy which could achieve higher, faster training time with an efficient model throughout different heterogeneous cases. Now, the question is there a way we can achieve faster training with a higher accuracy consistently for different heterogeneous cases? To answer this question, we propose an adaptive tier selection policy. The idea here is to adjust the selection probabilities of different tiers throughout the training process to improve the training time as well as training accuracy. First, we start with assigning equal selection probabilities to all the tiers. Then we introduce credits. Credits are training budget, which defines how many times a particular client can be selected throughout the training process. Ideally, you want to assign less credits to the slower tiers to limit their participation in the training process. First, we select a tier based on the adaptive tier selection policy, and then we decrement the credits by 1. And then further, clients are selected within their tier and ask for training. Once the clients finish their training, they share their models with the global model, which aggregates the model and shares the aggregated model with all the participating devices, which further evaluate the performance of the model locally on their test data, and then they share the accuracy with the global aggregator, which further utilizes these accuracies to adjust the tier probabilities by giving priority to the tiers with lower accuracy. As the lower accuracy indicates lower participation, we want to increase the participation of such tiers so that the model biasness can be reduced. Hence, once the model probabilities are adjusted by giving priority to the low accuracy tiers, we select the tier next by updated tier selection probabilities. And this process continues until we complete the training. One thing to note here is once a tier reaches a credits of 0, it will be excluded from the training process. The key idea behind adaptive tier selection policy is we want to prioritize the low accuracy tiers such that we can increase their participation, which further gives us reduce in biasness for the overall model. We also want to assign less credits to the slower tiers, which can further reduce the number of training time being selected and eventually leading to improved training time. By combining both of these ideas, we can strike a balance and achieve an efficient model with lower training time. To evaluate the performance of the proposed tier selection policy, we evaluated the performance first on different data quality heterogeneity, and we evaluated the performance against vanilla and uniform. When we compare the performance in non-ID2 setting, we observe that TIFL, which is adaptive tier selection policy, achieves higher accuracy compared to vanilla and uniform. We observe the similar trends in non-ID5 and non-ID10. So overall, TIFL outperforms vanilla and uniform selection policy in different non-ID settings. One thing also to notice here is during different non-ID settings, TIFL maintains a high performance throughout different non-ID settings. We further go on to compare the performance of TIFL against the static tier selection policy in 3 different heterogeneous cases: the class heterogeneity, amount heterogeneity, and combination of resource, class, and amount heterogeneity. In the class resource heterogeneity case, we can see that TIFL achieves almost 3 times improvement in training time, and in a combined case, we achieve 2 times improvement in training time. When we compare the accuracy after 500 rounds, we can observe TIFL can maintain a high accuracy different during heterogeneous cases and achieves either on par accuracy or higher accuracy compared to vanilla or federated learning. Then we evaluated the performance of TIFL on a real-world federated learning benchmark, which is LEAF. We select the FEMNS data set and we evaluate the performance in a combined heterogeneous case using different selection policies. When we compare the performance of TIFL in terms of training time for 2000 rounds, TIFL achieves almost 8 times improvement in the training time. When comparing the training time against the random and fast, we see that fast and random achieves slower training time compared to TIFL. However, when we compare the accuracy against TIFL for random and fast, TIFL achieves much higher training accuracy. On the other hand, when we compare the accuracy of the TIFL and vanilla, TIFL not only achieves 8 times speed up in training time, but achieves on par accuracy with vanilla federated learning. We also analyze the impact of tier-based federated learning on the differential privacy, as differential privacy is used in federated learning to guarantee the privacy for participating users. Here, instead of defining a global privacy budget, we assign a training budget to each tier, which can be easily controlled to allocate the budget and utilize the budget for different clients. The global aggregator keeps track of the budget utilization of each client, and the clients are excluded from the training process once they consume all the credits. Through this way, we can maintain a privacy guarantee. To conclude, TIFL achieves significant speed up in training time compared to vanilla federated learning. It achieves higher accuracy in all heterogeneous cases. It being lightweight, it can be incorporated in any federated learning environment without any extra overhead. The key takeaway of our presentation is the adverse impacts of high levels of data and resource heterogeneity in federated learning can be mitigated by intelligent scheduling of training devices. Thank you.